For a vehicle moving in a straight line, which one of the following physical quantities could be determined by finding the gradient of its velocity time graph? We know the gradient of a velocity time graph is acceleration. So if it's acceleration, we need to look for acceleration. Done. The velocity time graph below represents the movement of a train on a horizontal track. What is the average speed in meters per second of the object from 0 to 15? Well, let's first look at average speed. Average speed is equal to distance divided by time. So we need to first work out the displacement or the distance. Remember, this object is going on a straight horizontal track, so the distance and the displacement are the same thing. So first let's work out the area underneath this graph, and when we do that, we're going to get a rectangle at 10 times 8, which is going to be 80, and that is going to be plus half of a base, which is 7, times by 10, which is going to therefore be equal to 35, and I land up with 115 meters. I have to divide that by the entire time, so I divide that by 15 seconds. And that is going to equal 7,67 is the average speed, so it's meters per second. Which of the following velocity time graphs shows the motion of a body which falls from rest from the top of a building and eventually reaches terminal velocity? Now remember that any object that falls from rest is under gravitational acceleration. So it's going to be 10 meters per second squared is the acceleration. What happens simultaneously is that there is air resistance, and that works against the motion all the time. So what happens is, instead of accelerating at 10 meters per second, the acceleration slows down a little bit. And actually what you've got is you've got the downward force of gravitational acceleration, or if you prefer, the downward force is often known as weight. And acting against that downward force is an upward force of air friction. Air friction keeps getting larger and larger, so the acceleration keeps getting less and less, because there is going to be, slowly but surely, more opposition to the downward force of weight, until eventually there is zero acceleration. Zero acceleration does not mean that this object is slowing down or that it has stopped. It just means that it is going at a constant velocity. So initially we've got a lot of acceleration. The acceleration slowly gets less. Remember that a velocity time graph, the acceleration is equal to the gradient. So the acceleration is going to get less and less and less and less until it flatlines. So A is your correct answer. Which of the following acceleration time graphs refers to a free-falling object? When an object is in free fall, and we're not talking about terminal velocity and we're not worrying about air resistance, generally any object that is in free fall will be free falling at 10 meters per second squared, no matter what. So the minute it's in free fall, the acceleration doesn't change, it stays the same. Which of these graphs represents an object which is first subjected to an acceleration and then moves at constant velocity? So first there's some acceleration, and then, so it's a sudden thing. It's not gradually becomes constant, it's sudden. So we've got some acceleration, increasing acceleration. It's first subjected to a positive acceleration or an acceleration, not that you had any choices of negative accelerations. And then suddenly we've got constant velocity, no acceleration. Or the acceleration remains completely constant. So D is going to be your correct answer. If an object moves in a straight line, the distance covered is equal to. So distance is, we've got gradients and areas over here. Remember what distance is equal to. It is like displacement if we're moving in a straight line, and therefore distance is going to be the area under the velocity time graph. So let's look for that area under velocity time graph. C is your correct answer. Okay, that one we had already done. Referring to the velocity time graph alongside, the magnitude of displacement, its velocity, and its time. So displacement is going to be the area under the curve. So we've got a rectangle and a triangle for the first 20 seconds. We've got a big rectangle actually. So let's go. Base, the full base, 20, times the height, the full height of the rectangle, which is 6. And I land up with 120 meters. This little triangle over here is going to be half of the base, 10, times by the height, 6 to 9, is going to be 3. So we get 15 meters, and therefore if I add those together, I land up at 135. A train decelerates at a constant rate during a period commencing at t equals 0. Which of the graphs below represents displacement of the train? Decelerating means velocity getting less. If the velocity is getting less, the gradient of a displacement time graph will be decreasing. So where do we have a decreasing gradient? This is a flat line. This is a constant gradient, negative but constant. Positive and constant, positive and constant. Here, watch my gradient. Line, 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 line. It is a decreasing gradient. So that is my correct answer. The velocity time graph represents the motion of a motor car which begins to move easterly. All of the journey above the line, that is all east. The minute I get to point D, the object stops and changes direction, and everything below the line is west. So in other words, from D to F is going to be westerly. A rock is dropped vertically from a high cliff. If air resistance is ignored and the rock does not reach terminal velocity. So in other words, we're going to keep going at 10 meters per second squared all the time. Which of the following graphs is the relationship between velocity and time? Velocity and time, acceleration is constant. Acceleration is gradient. Where's my constant gradient? Acceleration is also constant. So I am looking for a positive 10 meters per second, and that is represented by, 10 meters per second squared, that is represented by C. Steel ball is rolling down a ramp with a constant acceleration. That means that on a velocity time graph, my gradient would be constant. But if it's speeding up, I need the velocity. What does that mean? Velocity increasing. What does that mean for displacement time? It means that gradient must be increasing. And if gradient's increasing, watch over here. Shallow slope, steeper, steeper, steeper. That is an increasing gradient. C is your correct answer. A ball is thrown vertically upwards. Which of the graphs best represents the acceleration of the ball while it's in the air? Remember what acceleration is equal to? 10 meters, or 9,8 if you prefer, 10 meters per second squared downwards all the time, never changes, and therefore it's got to be a constant value. This is acceleration on that graph. Constant value, C is your correct answer. The motion of two objects, A and B, is shown in this displacement time graph, and it shows what? Well, A is definitely more gradual than B. If it is a displacement time graph, that means that A has got less velocity, less gradient, than B, which has more. So A is moving more slowly than B is true. What about the rest? A and B are accelerating No, they've both got a constant velocity, so they're not accelerating. They are moving at a constant velocity. A and B will collide. No one says anything happens after that point, so who knows what's going to happen. If there were arrowheads on there, they might collide, but they don't. Both A and B begin moving from rest at the same instant. No one said they started from rest. In fact, they might have started with the same velocity that they have got. And the last one, a ball of putty is dropped from a height of 20 meters. It does not bounce and it strikes the ground. Which graph represents the displacement of the ball? Remember, it is under gravitational acceleration. Therefore, what is it doing? It is speeding up. Velocity is increasing. In a displacement time graph, velocity is gradient. So the gradient has to increase. Gradient getting steeper and steeper and steeper. Then the putty hits the ground and it just stops like that.